Now our R of t function, which you might have glimpsed accidentally at the end of our last clip, I've written it out. I've simply added the R1 and the R2 vectors, and we add the I components to get the I component of the sum. We've added the J components to get the J component of the sum. We can take the derivative of this function. And what does the derivative of this function tell us? Well, R of t is the position. The derivative of a position function, as we'll see in more detail, is a velocity function. So if we take the derivative of this function, we're going to get the function that tells us how fast and in what direction this thing is moving at every instant. Now, how fast tells us how quickly we're approaching whatever we happen to be looking at if we're looking straight ahead. Now that keeps changing. What's straight ahead keeps changing rather rapidly at some points. And we could ask a question of when is that point of our visual focus moving most rapidly? Interesting question. And we're going to be equipped soon to be able to answer that question. And also, are we speeding up or slowing down along that direction? Furthermore, are we being turned more or less quickly? All these things can be answered by considering the derivative of this function. So what's the derivative? Well, let's write this as r prime of t. And it's going to be a little bit longer than the r of t, so hopefully we can get it on the paper. The r prime of t function is just obtained by taking the t derivative. So cosine of pi over 3t has derivative what? Negative pi over 3 times the sine of pi over 3t. That's going to be multiplied by 10. So we're going to end up with negative 10 pi over 3 times the sine of pi over 3t. And the derivative over here is going to be derivative cosine of 2 pi over 3t is 2 pi over 3 times the negative of the sine of 2 pi over 3t, and that's going to give us negative 6 pi over 3 times the sine of 2 pi over 3t, and that's times our I vector. Now that's a relatively straightforward derivative. It's a little messy, it's a little long, and things can get much messier and much longer, and as we will see, they can do so rather rapidly. But this is going to be the I component of our velocity vector. We can combine these signs using trigonometric identities and learn more about the behavior of this I component, but we're not going to worry about that for right now. We'll just get the derivative. I've also in this step and this step eliminated the unit centimeters. We understand that if the time is in seconds, the position is going to be in centimeters, and just for brevity, we're not going to write out keep writing out the centimeters, and we're not going to write out the radians per second on the pi over 3. We've implicitly not done so already. Okay, anyhow, the derivative of the J component is found equally easily, and we see that that's going to be 10 pi over 3 cosine pi over 3t plus 6 pi over 3 cosine of 2 pi over 3t times j. Now, of course, there's simplification. 6 can be divided by 3 and so forth. And we're not going to worry about the details of that right now. You should be able to simplify expressions to some extent. And hopefully you've had the trigonometric identities, so you have some idea of how these things can be combined. Again, just mention that can be done. We're not going to worry about the details at this point. In any case, this is the derivative of our vector function. We could also ask the question then, just how fast are we moving at each point? We're moving, at any point we're moving forward, but we're also moving to the side. And how does that reconcile? How do we get our speed at a given instant? The speed is not difficult to represent. It's a little messy, but the speed at any given instant is just the magnitude of our velocity. Our velocity is r prime, so the speed at any instant is the magnitude of the r prime of t vector. Now, what's that look like? If we write it out, that's going to be the square of the I component plus the square of the j component added together, and then taken the square root. Okay, so the speed is what? Let's get a big square root sign because we're not going to be able to write this all at once. This is going to be negative 10 pi over 3 sine pi over 3 t minus six pi over 3 sine of 2 pi over 3 t quantity squared plus quantity 10 pi over 3 cosine pi over 3 t plus 6 pi over 3 cosine of 2 pi over 3 t quantity squared. We'd have to expand these squares, obtaining 3 terms for each, so we'd have a total of 6 terms with squares of sines and products of sines of different arguments, and same with cosines, and it would be kind of a messy expression. And what if we want to ask the question, when is the speed, when and where do we move fastest? What would we have to do? We would have to take the derivative of the speed so to maximize a quantity, a function, we take the derivative, set equal to 0, etc. And I'll leave the etc. to you. So we have to expand these squares, or, well, one way or another, we have to take the derivative of this expression and figure out when it's 0. That would be really messy. Nobody's going to ask you to actually do that. But we see that starting with a fairly simple model, we can get into a question that gets really, really messy. Not particularly difficult, just really messy. And we get these expressions that can be difficult to interpret. Most of the calculations we ask you to do in this chapter are quite a bit simpler than this, although some of them do get pretty involved.